Hi everybody, welcome to Multirate Signal Processing, and this is a demo for sampling. So here you can see the beginning of the slides as they are in Moodle 2, but we also have a nice demo, or rather a tutorial in Colab, which you can see here. So if you work through Colab, you also have the video snippets, and you also have code examples which you can work through. So most code examples work fine in Jupyter Notebook or Colab, except for the real-time audio examples. And I have quite a nice real-time audio example, a Python program which takes an audio signal from the microphone live, then does filtering optionally and sampling, and you can see the result on a live spectrogram waterfall. So basically what it does, it demonstrates what's happening here in this example spectrogram. So when you have the input from the microphone, you have this example spectrum, for instance. Say I'm whistling into the microphone, then you get a certain frequency and harmonics, and that it's not really similar to this, but it's more or less band limited. And when you do the sampling, then those spectral copies appear. And this is what you can easily see in the spectrogram waterfall. And this demo also does the reconstruction and playback. So you can actually listen to how those spectral copies sound like when you don't filter them out. So sampling, downsampling done right, filters those spectral copies out so that they don't appear at the output. But this demo allows you to turn on and off the low pass filter, which removes those spectral copies. So originally, before downsampling, you would make sure that this is a low pass signal to limit it to this span here so that the copies don't overlap. Then you would do the downsampling, which creates those spectral copies. I should say downsampling with zeros between the samples that we keep still in there. So the total sampling rate is still the same. Or you could say you have downsampling followed by upsampling, and then this upsampling inserts the zeros after each sample. So in this demo, the zeros are just kept between those samples. So this is then the signal that you can listen to, and you can also listen to how it sounds when the filter is turned on and off. So let me go back to my slides. So here we have it. So here's this example. It's called Pyrex back waterfall sampling. And here you can also see the processing steps that it's doing. So originally you just have a pass-through, right? None of those blocks is present. You have a waterfall spectrogram that shows the signal. Here's the microphone and here's the speaker. And then you have the option using the keyboard to turn sampling on or off using the key S. So here's an example of 2. In my demo, it's actually 8 to make it more easily visible and audible. So when you turn the sampling, downsampling, and upsampling on, then you will get those spectral copies that you see here. So here this was original. Then here you have those spectral copies which turn into alias components. And only if you apply the low pass in the beginning and the end, you are more or less sure to get the original spectrum back. So here, this low pass in the beginning makes sure that there will be no overlap between the original and the spectral copies. And the low pass for after upsampling makes sure that it removes those spectral copies. So here's the example. So we have the downsample factor of 8, downsampling and upsampling. So that means keeping the zeros. I have a simple low-pass filter. This low-pass filter is not perfect. It's a very simple low-pass filter using an IIR filter. So we will see that there's still some of the spectral alias components left. And then it shows the spectrum in this waterfall spectrogram. And this is basically a short-time Fourier transform, or a DFT, to blocks of the signal. So it subdivides the signal into blocks, length 1024 or 2048, and then it applies the DFT to it, and then it displays the magnitude of the resulting DFT coefficients on the screen. And the magnitude is coded in color. So yellow means high magnitude, blue means a low magnitude. And the horizontal axis corresponds to the frequency. So left is 0, and to the right goes up to Nyquist, which means it only takes the first half of the DFT spectrum, because the second half goes from Nyquist to the sampling frequency. And then it shifts those spectral coefficients up. So vertical is the time. So the further up we are, the further into the past we go. So it shifts all those spectral coefficients up. So this means we also can see the spectral evolution of the signal. Yeah, and this is actually also quite useful to analyze changing audio signals like speech or whistling, for instance, which I will do in a moment. So here's my example. So I open a terminal window, which I already have here. And then I just started with Python 3, pyrec waterfall sampling.py. It also runs with Python 2, so without the 3 here. But it seems to run somewhat better with Python 3. So then I can start it. So here you can now see it, and it's active. So here you can see actually a short description. There's key S for sampling, toggling sampling on and off, meaning upsampling followed by downsampling. Then we can toggle a low-pass filter, which is the key F, using the key F as turning on and off. And in the end, for quitting, we have the key Q. It uses the sampling frequency of 32,000 Hz and has a downsample rate of 8. So right now you can already see the spectrogram here happening. So left is frequency 0, and to the right we have Nyquist. So you can see high frequencies there's bluish, so there's not much. Most energy is the middle, and particularly here in the low frequencies. So you hear my voice directly, and also after processing, that's why you have this echoey effect. So you can also see how whistling looks like in the spectrogram. Let me whistle. So here you can see my whistling. You can see to the right you have higher frequencies, to the left you have lower frequencies. So now let me turn on the sampling without low-pass filter. S. So now you see sampling is true. So now you can see the spectral copies, particularly when I'm whistling. So here you can see my whistling as before, but you can also see this mirrored version. And this is basically the spectral copy, the first spectral copy. You can here see the central part of the spectral copy, and this originally was 0. And we know that real valued signals have the negative frequencies just mirrored from the positive frequencies. So this was originally a negative frequency, which now appears close to the original. And this is also why it sounded like if I whistle up, then this goes down, right? So I whistle up, this whistle goes down. And you can also hear those further spectral copies. So they make the impression of being very artificial. So it's sounding like ringing and really easily audible artifacts. Also with the speech you can tell that it sounds unnatural. You have this chirpy voice which makes the speech quite unnatural. So that's why it's important to limit the spectral range first to the beginning here with the first low pass filter before sampling to make sure that the spectral copies will not overlap. You can see here this is the original, and here when I go up with the whistling they almost touch. So we have to make sure that they don't overlap, right? So that's why it's important to limit this frequency range at the input. And then after upsampling we have to make sure that we remove all those spectral copies before playback to avoid this chirpy ringing artifacts. So now let me do it again with whistling, and now using the keyboard F, the key F for toggling on the low pass filter. And now F, filter is on. So now it was hard to hear because much of the energy is lost because of downsampling and filtering, which you can also see because there's more blue here. But I could actually increase the volume here to hear it more easily. So you can still hear a little bit of this first alias component, the first spectral copy here, but not much. And this shows that I just used a cheap filter here because it's not really good with the first spectral copy, this first alias component. But for the rest, it actually is doing a quite good job. So all the high frequencies here, where you would have the alias components, the spectral copies, they are gone. So that works. So now I can also turn the sampling off to hear how it sounds. So sampling off. So first I have to activate this window, then I can switch it. So this feedback comes because I have too much energy from the microphone directly into the speaker. Then we get this feedback at the beginning, the system begins to oscillate like an IIR filter, infinite impulse response filter. So when you have too much feedback, you get an oscillating system. So here you are back without sampling, just with a low pass filter. And you can see it here, the high frequencies are gone indeed. What's left is the low frequencies, but those low frequencies are really muffling. Only the low frequencies remain. So that's a disadvantage of a low pass filter. So now it doesn't really make much of a difference if I turn on the sampling or not. So turning off sampling here, now I turned off, now I turned on the sampling. It's not much different except that the energy is now reduced because I removed most of the samples. So now it's back to normal, no sampling. And here, filtering off. So now it's back to original. Okay. So that was the demo where you can see and hear all the combinations of filtering and sampling. So we saw when we turn on sampling, we clearly hear the aliasing artifacts, and we also see them as spectral copies in the waterfall spectrogram. When we turn on the low pass filter, most of the aliasing artifacts are not audible anymore, and we also don't see most of them anymore in the waterfall spectrogram, but it also sounds more muffled because now the high frequencies are missing. Okay, that's it for this live demo. we have more examples, which are also shown in the tutorial, in the Jupyter Notebook tutorial. And you should also always try out all the examples in Python yourself, because that gives you a better feel of those effects. And also it shows you if you can actually run it on your computer. Okay, so thank you for your attention and see you next time.